Okay, so this is actually chapter 11. I know on your notes I didn't change that. The old book, it was in chapter 10. But this is chapter 11. And again, like I said before, this is a combination of taking the mole and combining it with chemical reactions. So both of those things we've done so far, we're going to put them now together in what's called stoichiometry, which is where we are looking at mass and or volume, as well as Avogadro's number, counting. We'll talk about that in the notes tomorrow. So we can throw in counting problems as well. It's just not as common, like I said, in the mole unit. You know, we don't do a lot with Avogadro's number because there's not really, ways to measure that. So the majority of stoichiometry problems look at mass and or volume relationships between different substances in a chemical reaction. And that's what makes it different than just our mole chapter. When we first started out this semester and we were doing mole problems, we were just looking at one substance, an individual element or a compound, but we were just converting back and forth between mass, volume, or particles of a single substance. Here with stoichiometry, we're doing the same thing, but we're going from one substance in a chemical reaction to another substance. And we can look at one reactant and compare it to another reactant, or we can look at a reactant and a product to a reactant, or a product to product. So we can look at any combination of substances in a chemical reaction and compare masses, which is what we're going to focus on today. And then tomorrow we'll talk about volume and even using Avogadro's number as well. So because we are going back and forth between different either individual elements or compounds in a chemical reaction, the way we're able to do that is through the coefficients that we put in there when we balance the chemical reaction. So those coefficients from your balancing, which is why last chapter was so important, those are used in what we refer to as the mole ratio. And that's mole ratio is what lets us convert from whatever substance we're starting with and takes us over to the new substance that we're trying to solve for. And so the way we set up the mole ratio, so for the mole ratio, we have the however many moles of what we're trying to solve for over the number of moles that we were of our given. And those numbers, these numbers those are our coefficients from the balanced chemical reaction. So again, as I've said many, many times, if you have your formula wrong, that could cause you to balance the reaction wrong, and now that's going to cause you to have wrong numbers possibly in this mole ratio. So again, luckily, as I said, I think most everybody has finally been improving on their formula, so hopefully that won't be an issue. Now, first, before we get to doing mass problems, which those are the most realistic type stoichiometry problems, we're going to start off simple and just look at how we can go from moles of one substance to moles of another. And again, kind of like Avogadro's number, we really don't ever measure in moles, but this is just to kind of warm you up and see kind of how we set it up before we get into more complicated type problems. So if we're starting with moles of one thing and ending with moles of another in a chemical reaction, first, regardless of any stoichiometry problem we do, we're always going to write a balanced chemical reaction. So that's always going to be our first step. And then again, for this first example that we're going to do on the next page, we're just going to start and end with moles. So if our given is in moles, we set that up, and as you'll see when we do the problem on the next page, the more you label, we talked about labeling units in the mole chapter. Now I'm even going to recommend labeling the substance as well, so we'll see that. So we're going to start with whatever, bless you, substance and unit that we're given. And then, again, to convert that to the substance in the chemical reaction that we're solving for, that's where we use this mole ratio here. That will convert us from our given into our unknown. Now again, we're not going to do a whole lot of problems that we're starting and ending with moles, but I just wanted to show you how this is as simplistic as we can get with stoichiometry problems. So again, here's just a chemical reaction where we're going to start moles of one substance and convert it to moles of another. This one says how many moles of hydrochloric acid are produced by 3.75 moles of lead 2 chloride reacting completely with excess nitric acid. Now, word problems are back, so just like we did in the mole unit, got to pay very close attention to the word problem, what information is giving us, what information is asking us to solve for. And so in this case, first step is we want to write out and balance our chemical reaction, and I'll usually always give you a little RxN to remind you to write that out and get it balanced. So reading through here again, it's asking us how many moles of hydrochloric acid are produced. So that's going to be a product. And then it says we have lead 2 chloride reacting completely with excess nitric acid. So one of our reactants is lead 2 chloride. And then we have nitric acid. Now it says excess. A lot of times, it may not always say that, but a lot of times if there's a second reactant, it may say excess. Don't worry about that right now. Later on, as we get further into the chapter, we'll talk about what that means and some other stuff that we have to do when we don't have excess of the other reactants. So so those are our reactants, and then it tells us that one of our products is hydrochloric acid. But it does not, and it may not ever even tell you either of the products. So again, that's where last chapter comes into play of knowing I've got a salt and an acid, so I'm going to do a double replacement and trade the hydrogen and the lead to form a new salt, new acid. So here's our new acid, and then our new salt would be the lead 2 nitrate. Now with these problems, turn your eyes a little bit. With these problems, if we have a volatile acid or a volatile base, unless it is having you solve for one of the things that it breaks down into, like water or whatever, just leave it like this. You don't have to try and decompose the volatile acid or volatile base. So just leave it as is. And then we do need to, again, make sure we balance it. So to balance, we need a 2 and a 2. Okay, so there's our balanced reaction. Now the other thing I like to do, you don't have to do this, but I think it's easier to figure out how to set up the math part, is I like to, once I get my reaction written out and balanced, I like to go through and label what am I given, what am I solving for. So I'm solving for moles of hydrochloric acid, and I'm given 3.75 moles of the lead 2 chloride. So again, you don't have to do that, but I think it's helpful to know, okay, so we've got our reaction written out. Now the first step is to take our given, which is, in this case, the 3.75 moles of lead 2 chloride. And again, I'm going to label not only my units, moles, but also the compound. Because with stoichiometry, we're now switching compounds. So the more you label, I think the easier it will be on you. So that's our first step. We've got our given. And then if we're in moles, then we can switch over to our other compound by using this mole ratio. And in fact, mole ratio is so important that Mr. Mauger always, when he was a teacher here, always made his students write the mole ratio in red because of how important it was. So our mole ratio, we put the moles of our unknown, so that's here, this is our unknown, and from our balancing, that's a 2. So we have 2 moles of HCl in our numerator, and then we put the number of our given moles in the denominator. So from our balancing, you don't have to write the 1, but it's understood. There's 1 mole of PbCl2. So the 2 came from here, and this 1 came from up here. And again, labeling your compound will help ensure that you've got your mole ratio set up right, because we want moles of lead 2 chloride in this case to cancel out. So we have to have this down in the denominator, because if it was up in the numerator, they wouldn't cancel. So that cancels out the lead 2 chloride, and that gives us the units that we're trying to solve for, moles of hydrochloric acid. So again, the more you label, the more helpful it is. And then we're ready to solve, where in this case, we just multiplied 3.75 times 2, which gives us 7.50 moles of hydrochloric acid. Okay. And again, you're not going to see a whole lot of mole-to-mole stoichiometry, because we really don't measure anything in moles. It's just a way to get from one thing to another. But does everybody see how we did that? How that was set up? George?
So if there's 3.75 moles of lead chloride, why is there only 1 mole on the denominator of the...
That's from our balancing. Yeah. So the mole ratio, the only numbers you can put in the mole ratio come from your balancing. Yeah. And what that's showing from our balance reaction, these coefficients show us relative amounts. So for every 1 mole of lead 2 chloride, we have 2 nitric acids, 2 hydrochlorics, and 1 lead. So it's just showing us a ratio, and so that's what we put in here. Good question. Anybody else? Okay, well then let's move on to the more realistic stuff, and our main focus of today, which is mass stoichiometry. So probably 75% of the stoichiometry problems we'll do will be mass-to-mass stoichiometry. So, as you can probably guess, mass-to-mass stoichiometry is where we're starting with the mass of one substance and converting to the mass of another substance. And again, we can go from reactant to product, we can go reactant to reactant, product to product, product to reactant, so we can do any combination. It does not have to, we do not always have to start with a reactant and solve for a product. That's a lot of them, but we can solve for any substance in the chemical reaction. And in this case, with these types of problems, we're starting with the mass of one and converting to the mass of another. Now, thinking back to our mole chapter, when we were dealing with masses, to get to moles or get from moles to mass, we had to use the molar mass of the substance, which means the periodic table to look up the masses, and you need to make sure you got the right formulas so you can add them up correctly. And just like we did in the mole chapter, we're going to carry our molar masses out to the tenths of a gram. Okay, so anytime there's something other than a 0 in the tenth spot, make sure you include that because that will affect your answer. Okay, so again, the steps, first step, always to write a balanced reaction. That's going to be the same no matter what type of mole problem, stoichiometry problem we're doing. But then because with these problems we're not starting with moles, we're starting with mass of our given. We first have to convert our given from grams to moles, which as we did back in, what was that, chapter 10, that means we divide by the molar mass of whatever substance we're starting with. Then, so once that gets us to moles of our given, then we're ready for the mole ratio to switch over to the substance that we're solving for. And then if we also want to solve for mass of whatever it is, the other reactant, a product, or whatever the case may be, to convert that from moles to grams, we need to multiply by its molar mass. Okay, so, and that's what, just like in the mole chapter, that's what makes these type of problems the hardest, which is why I like to start with them so you can have the most practice with them. Because again, every compound is going to have its own unique molar mass based on its formula and their masses. Okay, so you're going to have to figure out a molar mass for your reactant and a molar mass for the product. They will not be the same. Okay, so that makes these a little more tricky to do. So here we have trying to figure out how many grams of ammonia, which if this were on a test or quiz, I would give you this formula. Ammonia is NH3, or nitrogen trihydride is the official name for it. Can be produced from the reaction of 3.41 grams of hydrogen and excess nitrogen gas. And it doesn't really matter what the states of matter. Don't worry about that. If it tells you that, great. If not, it's no big deal. What matters most is that you get the reaction written out and balanced correctly. So our reactants are nitrogen, which is diatomic, and hydrogen, also diatomic. So don't forget your 7 diatomics. And then it's going to form, again, ammonia is NH3. And then to balance, 3 and a 2. Okay, so there's our balanced reaction. And again, I like to label what I'm given and what I'm solving for. Again, you don't have to do that if you don't want to. But we're trying to figure out for this one how many grams of ammonia we can make with 3.41 grams of nitrogen. So again, I just do that to help figure out where I'm starting at and where I'm trying to get to. Which one is, oh crap, thank you. Wrong one. Yeah, it helps if you label the right ones. Glad you saw that. 3, I wrote it backwards, that's why. There we go. I just found that before I went through all that. Okay, so yeah, we're starting with 3.41 grams of hydrogen. We have excess nitrogen, which again, don't worry about that for right now. We just need it there to get everything balanced out correctly. So starting with the correct given this time of 3.41 grams, and again, I'm going to label it just so I know how to set up everything, my other ratios as well. Now, since we're in grams, we can't go right to the mole ratio. We've got to get this into moles first, like what we did in chapter 10. So to do that, we need 1 mole over the molar mass of hydrogen, which again, you probably remember it or will remember it shortly, but you know, looking it up on the periodic table, we have 2 times 1, so hydrogen's molar mass is 2. And so that will cancel out our grams of hydrogen. And now we're where we were with the last problem. Now we are at moles of hydrogen. So once we get to moles, then we're ready for our mole ratio. So to get us out of hydrogen and into ammonia, we want to put the 2 moles of ammonia in the numerator, and then the 3 moles of hydrogen go in the denominator. Okay, because we want hydrogen to cancel and we want to get into ammonia. So that will cancel out our moles of hydrogen, and now we're into moles of ammonia. And again, those numbers come from our balancing. And now for this problem, instead of stopping at moles, we want grams. So that again is where we need our periodic table and look up the masses, which nitrogen is 14, and then each hydrogen is 1, so 17 grams of ammonia for every 1 mole. Okay, so then that cancels out our moles, and that's gonna leave us, when we solve, leave us with grams of NH3. Does everybody see how I set that up? And again, the more you can label, the better. You know, we've got a lot of stuff going on here. We've got a lot of ratios. So the more you can label in your ratios, the better chances you have of making sure your ratios are set up properly so that, you know, grams will cancel here, hydrogen cancels here, moles cancel there. So again, you can label as much or as little as you want, but I see so many times where people have their ratios flip-flopped, and it's usually because they didn't label. Now, math-wise, you can multiply and divide any way you want, as long as anything that's in the numerator is being multiplied, while anything in the denominator is being divided. In this case, we have 2 things in the denominator, so we'll need to divide both of those. I like to do it all in one thing. It saves me from, you know, having to write down a number and then re-enter that and do it again, and that's where mistakes can occur. But again, you can do it any way you want. But I like to go across and do all my numerators, multiply them all together first. So 3.41 times 2 times 17. And then divide by 2, because that's in the denominator. And then divide again, because we have a second denominator here, by 3. That's not right. Let's try that again. And that gives us 19.3 grams of ammonia. Okay, so again, you can go about multiplying and dividing however you want. Just remember, numerator have to be multiplied, denominators have to be divided. Sometimes you only have 1 denominator, sometimes you may have two numbers in the denominator, just depends. And since we started with 3 sig figs here, with the 3.41 grams, I'll keep 3 sig figs there with the grams of ammonia. And again, if you went 1 more or 1 less, as long as you're rounding correctly, that's fine. Okay, but you got to show your reaction, got to show your factor labeling, how much you want to label of that factor labeling. That's up to you. Okay. Anybody have any questions?